Now let's take a look at distance time graph. This is the second section of Unit 7.5. So let's read this first page. Consider a car traveling in the following scenario. So the distance from town A to town B is 50 kilometers. And then the car goes from town A to town B in 40 minutes. The car stops at town B for 35 minutes. And then last but not least, the car then drives back from town B to town A in 35 minutes. So actually, we can represent these 4 bullet points in a graph. This graph, we call it the distance time graph. Okay, it is a graphical representation to show journey where the y-axis is distance and the x-axis is time. So let's take a look at this graph already drawn for us on the right. Let me highlight to you which bullet point represents which part of the graph. So the distance from town A to town B is 50 kilometers. And the car goes from town A to B in 40 minutes. So let me just highlight this in yellow. So this straight line up actually represents this 2 bullet points, okay? 50 kilometers, 40 minutes. Next, when a car stops at somewhere, that means the distance doesn't change. Okay, which means in a distance time graph, it will be represented by a horizontal line. So let me just write here, represented by a horizontal line. Last but not least, the last bullet point, the car then drives back from town B to town A in 35 minutes. So it's this downward sloping line here. 35 minutes is traveling back from town B, which is 50 kilometers away from town A. You'll drive back to the starting point at town A. So this is how the 4 bullet points are represented by a graph. Now let's move on to the second part of this page, speed at a certain period of time. So in a distance time graph, the speed, also known as the rate of change of distance over time. So let me just write the formula here. Speed is actually distance over time. It can be represented in this triangle that most of you might have seen before, DST. So speed is equals to D over T. Okay? So speed is also known as the rate of change of distance over time. Okay? And then this is actually the gradient of the straight line in the graph that you are given or you need to draw. So take note, gradient of the distance time graph is actually the speed. So let me just write here in red. The takeaway from here is gradient of a distance time graph is actually the speed. Okay? So let's look at the last part of this page, okay? So from the distance time graph given here, okay? So take note, starting position is at A, you're driving to B. If it's upward sloping, if it's downward sloping, you're actually returning from B to A, okay? So positive gradient, let's look at this yellow line first. If you notice, this yellow line is an upward sloping line. It means the gradient is positive. It is moving away from town A, which is the starting point. Let's now look at this blue color horizontal line here. When it is a horizontal line, the gradient is 0. The object or the car, in this case, is at rest and not moving. Last but not least, this downward sloping line where the object, or in this case a car, is returning back to the starting point. Negative gradient, returning back to starting point, in this case town A. So take note, when it's a downward sloping line in a distance time graph, it means it is returning to its starting position. So this is what it means, okay? Positive gradient just means it's just driving away from the starting position. Last but not least, let's look at this formula on the last part of this page, okay? Very important formula, okay? Questions like to ask the average speed based on the distance time graph. So if speed, let me just go back to this formula. If speed is distance over time, then the average speed is just total distance traveled over total time taken. So this formula is very important. Let me just highlight it. Average speed, total distance traveled over total time taken. Now let's take a look at this GeoGebra animation that has distance time graph. So take note, the distance along road in meters is represented by the vertical axis. And then for time is at the horizontal axis, and the units is in seconds. So I already enabled the road on the left of the graph, so we can actually see how the car travels from 0 to 10 seconds. I'm going to press play. So as you see here, the car will travel all the way until 100 meters, and then it will stop for a bit, and then travel all the way to 200 meters. So let me replay it again. 0 seconds all the way to 4 seconds, it will stop for a while at 100 meters and then continue on. So I'm going to enable the graph now, and then you can see how the car, as the car travels, how the graph is being plotted. So I'm going to press play again. So as you can see, at the fourth to 6 second, the car actually stopped for a bit. So that's why at 4 to 6 seconds, it's a horizontal line. So take note, from 0 to 4 seconds, it is a positive gradient because it is going away from the starting point. And at 6 to 10 seconds, still positive gradient because the car is still going away from the starting point. Now let's observe another GeoGebra animation with this car, the same as before, but now it will be traveling differently. Let's take a look. So all the way to 4 seconds, it will go back for a bit towards the starting position, and then it will go away from the starting position again. So let me just replay it again. So it's going away from the starting position, and at 4 seconds, go back a bit, reverse back, stationary, and then it will travel again. So let's take a look from 0 seconds with the graph. So how the graph is plotted based on how this car traveled. So at 4 seconds, you reverse back, and at 6 seconds, stationary, 8 seconds, traveling away from the starting position again. So do take note, when it's reversing back and it's going towards the starting position, there will be a negative gradient, downward sloping line from 4 to 6 seconds. And then if it's stationary, horizontal line, as you can see from the 6 to 8 second. And then at the 8 second, it continues traveling away from the starting position. That's why it is an upward sloping line to the 10 second. Now let's move on to the examples for distance time graph. Let's look at example 1 here. The diagram shows the distance time graph for a journey by a cyclist. So part A asks you to find the speed of the cyclist during the period represented by part 1 OA, part 2 AB, and part 3 BC. So OA, AB, and BC. So what we can do first, because to find the speed is actually the gradient, you need coordinates. So we can label coordinates for each point first. So A here will be 1, 20. B here will be 1.5. comma 20, and C here will be 3 comma 40. Now let's do A part 1. So to find the speed during the period OA, we need to find gradient. So speed equals to the gradient y2 minus y1 over x2 minus x1. Okay, so it will be 20 minus 0. So I'm using the y coordinate for A and the y coordinate for the origin over the x coordinate of A, which is 1, minus x coordinate of origin, which is 0. So you'll just end up with 20. Take note for the units, it will be distance over time. Distance unit is km, time is hour, so it's km per hour. Now let's move on to A part 2. If you notice, the distance here doesn't change. It is a horizontal line, so you can straight away write that speed equals to 0 km per hour because the cyclist was not moving. Last but not least, we have the speed for BC, so we can write speed equals, likewise, just find the gradient. Substitute the coordinates of B and C, so we'll have 40 minus 20 over 3 minus 1.5, and you will get 13.3 km per hour to 3SF. Now let's move on to part B. Find the average speed of the cyclist for the whole journey. So let me write out the average speed formula first. Total distance over total time. Okay, to find the total distance, what we need to do, we need to see where it ends off. So if you notice, the cyclist goes away from the starting point and away again. So it ends off at 40 km over here. So total distance is 40. The time taken will be total of 3 hours. And you will get 13.3 km per hour to 3SF. For example 2, please pause to try by yourself. And then when you're done, please press play to see the solution for example 2. So for example 2, okay, I will briefly go through. So for part A, the bus driver stopped to take a rest during the journey, which is this blue highlighted part here. How long was the stop? So if you zoom in, it's only half an hour, which is 30 minutes. So answer for part A, 30 minutes. Now let's move on to part B. Calculate the speed of the bus from point A to point B as highlighted in green. So you can label the coordinates for A and B first, calculate the gradient, and you will get 40 kilometers per hour. So take note, I'm following the units given in the graph. Last but not least, for part C, find the average speed of the bus. So take note, the bus goes away from starting point, takes a break, goes away from starting point again to 160 kilometers, and then returns back to the starting point. So that means the total distance is 160 plus another 160. Total time is 5, so 160 plus 160 over 5, you will get 64 kilometers per hour as the average speed. So this is for example 2. For example 3, please pause and try part A and B on your own. It's similar to the questions in example 1 and example 2. Once you're done, you can press play again. So for example 3 part A, you have to find Mrs. Brown's speed during the period represented by part 1 OA. So you're looking at this line. So likewise, the coordinates of origin and A already written down. You can find the gradient and you will get 83.3 meters per minute. So take note, the units for distance is meters, units for time is minutes, so hence meters per minute. And then for A part 2, you have to find the speed during the period AB. Likewise, I already written down the coordinates. So take note, because this is a downward sloping line, find the gradient first and you notice it's negative. The negative sign indicates Mrs. Brown is returning back to her starting point. So the speed, take the positive value, which is 55.6 meters per minute. Now let's go on to part B, average speed. Write the formula first, which is total distance over total time. Take note, because Mrs. Brown is going away from starting point and going back towards the starting point, you have to take 1000 plus another 1000. Total distance. Total time is 30 minutes and you will get 66.7 meters per minute. For part C, we have to describe briefly her journey as shown in the graph. We can use part A's answer. Let's look at OA. So OA here, you notice that the speed already calculated 83.3 meters per minute. So let me just highlight this blue part. Speed is 83.3 meters per minute. Okay, so you notice that Mrs. Brown walked at a constant speed. So over here, the speed is constant because gradient is the same throughout for 12 minutes. So we can write Mrs. Brown walked at a constant speed of 83.3 meters per minute for 12 minutes. That's the blue part. That's the blue highlighted part here. I'm going to highlight the other one in green. So to explain the part in green, we can also say that she walked at a constant speed of 55.6 meters per minute for 18 minutes. So 30 minus 12 will give you the remaining 18 minutes. So for the second part, you can explain it like so. So take note, the keywords will be constant speed, the values of the speed, and then the time taken. Now let's look at example 4. So take note, Betty walked from P to Q, which is 6 km apart. So over here is the distance time graph of her journey. Let's do part A together. So find her speed at 1430. So take note, 1430 is between 1400 and 1500. So over here. So do note that this is in the 24-hour time format. Okay. So this means from 1300 to 1400 is actually 1 hour. 1400 to 1430 is actually just half an hour. Maybe I'll just write half hour, which is better. Okay. So do note the units here for time is actually in hours. Okay, so find Betty's speed at 1430. So take note, this point is actually on this line here. Okay, so this point will have the same gradient as any point on the line here because they're on the same line. So what we can do to find Betty's speed at 1430, we can actually find the gradient of the line joining this point and also this point. That's where we'll get the speed at this point at 1430 as well. So let's write gradient equals to, I'm gonna write the coordinates of these 2 points down first. Okay, so take note, the x value will not be 1400, it will be 1 hour instead, because from 1300 to 1400 it is 1 hour. So this will be 1,6. Next up, this from 1300 to 1600 it will be 3 hours, so 3,0. So for part A, the gradient will be 0 minus 6 over 3 minus 1, and you'll get negative 3. So you can write hence speed is 3 kilometers per hour. So take note, I repeat again, negative is because Betty is walking back to the starting point. So as what I've written here, negative value for gradient because she's walking back to starting point. So do pause the video now to try part B and C yourself. Press play again to see the final answers and check your workings. Now let's take a look at part D of this question. So do take note, please check your answers and solution for part B and C yourself. For part D, now a new person introduced called Jackie walked at a constant speed of 6 kilometers per hour. Take note, this is from Q to P. Betty walked from P to Q. So I drew a diagram here for you to understand better. Town P, Betty walked from town P. town Q, Jackie walked from town Q. So they are walking in opposite direction. Do note also Jackie started walking 30 minutes later than Betty. Now let's do part 1. How long did it take for Jackie to reach P? Okay, how long, meaning the time taken. So let me just draw the triangle to represent the relationship of speed, distance, and time. Okay, so take note, to find the time taken is actually distance divided by speed. So D over S. So let me just write here. Time taken, distance over speed. So the speed of Jackie is given. Distance we also know as well, because question has given P and Q are 6 km apart. So 6 over the speed, which is also 6, and you will get the time of 1 hour. Now let's look at D part 2. We need to draw Jackie's distance time graph on the same axis here. Okay, so we have a crucial information already. We know that time taken for Jackie from Q to P is 1 hour, and he started walking 30 minutes later than Betty, which means he started walking at 13:30 because Betty started walking from 1300. So let me just mark where 13:30 is first. And Jackie finished the journey in 1 hour. So 13:30, 1 hour later will be 14:30. So let's mark the time out first. We know that Jackie started walking from Q, town Q. So town Q is 6 kilometers away from town P. So take note, the y-axis here is actually distance from town P. So at 13:30, he's actually 6 kilometers away from town P because he was at town Q. And then he finished his journey 1 hour later. He reached town P 1 hour later. So I can plot a point here. 13:30, 6 kilometers away from town P, which is town Q. And at 14:30, he reaches town P. So I can connect these two points together to form the line, and then I'll label this line as D part 2 Jackie's line. So that's how you do D part 2. So for D part 3, when and where did Betty meet Jackie? So they meet at the intersection point over here. So I'm just gonna draw a dotted line down to the time axis to see what time they meet. So if you notice, it's about 3/4 away from 1300. So this 3/4 will just mean 1345. Okay, and then the distance here is halfway through 3 and 6, so it will be 4.5 because 6 minus 3 divided by 2 is 1.5. You can take 1.5 plus 3, you will get 4.5 kilometers. So the coordinates here will be, take note, 1345 minus 1300 will be 45 minutes. I'll just put 3/4 hour because this will be, the time units is in hour. So 3/4, 4.5. Okay, so when and where did Betty meet Jackie? Betty met Jackie at the time 13:45 or 1:45 p.m. after Betty had walked 4.5 kilometers from P. So Betty had walked 4.5 kilometers from town P. So that's how you explain for D part 3.